Swayam Prabha. Digital India. Educated India.
So, let us look at what is happening here geometrically. Effectively, what is being claimed by this particular by this particular equation, the boxed equation. Let us try to understand this. Okay. So, for to understand this, we first need a basic idea of what the role of the derivative of a function, derivative or the gradient of a function is. What does it tell you about the function? So, any function, if it is a function of say n variables, I can just instead of plotting it in a way where I look at the n variables on the as independent variables and the value of the function in another axis, instead of that I can look at the contours of the function, right. So, I can plot a function like this. Suppose these are the contours of f0. Okay. So, suppose these are the contours of f0. So, what does this mean? So, this means that this is the locus of points x. So, a contour like this is a locus of points where f0 is a constant. So, it is all points x such that say f0 of x is equal to c, some constant c, and as I vary c, I will keep getting different contours. These contours will obviously not intersect because they correspond to different values of c. Okay. And you may or may not get concentric contours like this, that depends on the shape of the function. I am just taking for simplicity this is how that the contours look like this. Now, what is the role of the derivative or the gradient? So, if I take a point like this here and I say, well, the gradient is a vector as long as x itself. So, I can draw the gradient with origin shifted here, suppose. So, this is the vector grad f0 of x, but I have just instead of what I have done is I have just shifted the origin of that vector to this point x itself, to this particular point. Likewise, at this point, this would just for indication, I am just drawing the gradient in this sort of way here. If this is my x, then if this is the point x, then this is the gradient. This is the gradient. Now, what does the direction to which the gradient is a vector? It's pointing in a certain direction. If I shift its origin to x, it's pointing in a certain direction. What does that direction tell me about the function? So, so first thing is the gradient is always normal to the contour. Okay. So, the gradient, if the function is differentiable, then is always normal to the contour. Why is that? Yeah, right. So, contour comprises of points where the function value is a constant, right. So, the gradient and whereas, so effectively what must be happening is that so the gradient is, you can think of as if in the scalar case is basically the derivative. Effectively, the derivative along these points has to be as you travel along this should start vanishing, right. So, you should if you take the rate of change of the function as you travel around the contour, that should vanish. What that it means in Rn is that the gradient itself must be orthogonal to this to the direction in which you are traveling while you are on the contour, all right. So, the gradient is always orthogonal to the contour. So, the gradient is orthogonal to the contour, but which direction does it point in? So, there are two orthogonal directions, right? One is a direction here and the other. So, for example, if this is a point, I could talk of this orthogonal direction, I could also talk of this orthogonal direction. Yeah. So, this is the other thing about the gradient. So, this direction, the gradient always points in the direction of increase of the function f0. Okay. So, so the way to see this in this contour plot is to see, suppose here C is, let us suppose this C is equal to say 100, and this C, inner C here is, suppose this one is say 110. So, the gradient is pointing inwards, means it is pointing towards the direction in which the contour values keep increasing, right. So, if this was reversed, if this was not 100, say it was 90, if the function values were decreasing as you went into inner and inner contours, then the gradient would have been pointing outwards, outwards in this direction. Okay. Inwards or outwards, it depends on what is happening to the function value. You cannot tell that from just looking at the shape of the contours. Okay. So, the gradient is always pointing in the direction of increase of the function f0. Okay. So, now let us come back to this boxed condition. What is this condition saying? It is saying that if you take the derivative of the function f0, it is given as it is a linear combination of the derivatives of the derivatives of the constraints, right. Okay. So, what does this, what would that mean? That means the direction in which f0 was increasing at x star, if you look at the point x star and look at the direction in which f0 was increasing, okay, that is the direction of the gradient. If you look at that direction is itself a linear combination of the directions of the gradients of the constraints. Now, what does that further mean? It is satisfying the constraints also, yes. So, you are on the surface, correct. You are on the surface, you are on the surface, and then what does that say? So, okay, so let very good. So, let me write it in this sort of way. So, the linear, so once we have linear independence of the derivatives, what we can say is that the tangent plane to this surface, or the common surface area, common area in all surfaces, right. The tangent plane, that is the tangent plane the feasible region at x star is given by all directions d such that so it's all directions d such that if I take the derivative at x star, that times d, or equivalently, let me write this in terms of the gradient at x star transpose d, this is equal to 0 for all I in n. So, if you take those directions d for which are such that such that the gradient is such that they are orthogonal to all the individual gradients. This means if you take the subspace spanned by these gradients, D is orthogonal to that subspace, right. So, because it is orthogonal to all the individual gradients. So, that those D's are your tangent directions. Okay. Now, if your f0 of x, okay, if your f0 of x, okay, if your f0 of x lied in that tangent direction, then what did that mean? If the gradient of the objective was in that tangent direction, what would that mean? What it would mean is that you could increase your function while also gently going along the tangent to your surfaces. Means there was scope for you to be on the surface and at the same time increase the function further. So, there is this surface that is, so they have all these surfaces that are intersecting. The tangent to them is orthogonal to the space, to the subspace formed by the gradients of the constraints, and your objective gradient also lies in that subspace, because it is a linear combination of the gradients of the constraint, right. So, the directions that you need to go in order to be on the surface is orthogonal to the direction in which you need to go in to increase the function. So, this is the compromise that gets reached here. Essentially, when you if you are at a local maximum of this problem, then this has to be true, that you cannot both continue to be on the surface and also increase the objective value further. Because if you could increase the objective value and also be on the constraint and stay on the constraint, then the gradient, which is the direction in which objective value increases, that gradient would have some positive component on the subspace in which you need to be to remain on the surface, right. So, if you had to remain on this particular surface, and then for that you need to travel along a tangent to it, but your gradient is pushing you in this sort of direction orthogonal to that tangent, right. So, the gradient here is a linear combination of the gradient of the objective is a linear combination of the gradient of the constraints, whereas the tangent space is orthogonal to the subspace formed by the linear combinations of these constraint gradients. Is this clear? So, this is basically the condition that is being expressed here, that these are two orthogonal directions, and if there was even a slight component between of the gradient of the objective onto this subspace, then there would have been scope for you to travel further in that direction, and you would have potentially gotten a better objective. Okay. So, that is what this condition effectively says, that it's just expressing that the very fact that you are at a local minimum means that this is the very least, local maximum means that this is the very least that must be true. Is this clear? Okay. So, this is the geometric interpretation behind what is what's happening here. Now, can someone suppose if I ask you a related question, suppose what if I instead of a maximization, which is what I have here, I have a maximization problem here written here. If I had a minimization problem, how would this change? So, I could just replace f0 by a minus f0, and that would correspond to minimizing the function f0. So, you are maximizing the negative of f0. f0 gets replaced by minus f0. All the other conditions are not perturbed by this. What I would get is a negative sign sitting out here, right. I would get a negative sign sitting out here behind next to the gradient here. But then that negative sign I can absorb in my definition of lambda star itself, because this condition simply says there exists some lambda star. So, I can absorb that into the lambda stars, and the condition would still look the same, just that the lambdas would have reversed their sign. Okay. So, but there exists some other lambda star, that is all it would mean. Okay. So, this condition would not change even if I had a minimization problem. Now, that gives you a clue about what is going on here. It tells you that this is actually a very weak condition. It works for both maximum as well as minimum. So, the very fact that you have found lambda star and an x star such that these equations are satisfied does not mean that you have actually got to a local maximum. You could as well have got to a local minimum, right. So, geometrically the same compromise that I just mentioned, that you cannot go in the direction of increase of the function because the gradient should not have a component in that direction. Likewise, if the gradient had a component along that tangent space, then the negative gradient would also have a component, and you could go in the direction of decrease also, right. So, the same argument can be worked for the minimization also. So, the point, so this condition tells you that, well, there exists such lambda star such that these equations are satisfied is both for local maximum as well as for local minimum. Okay. So, to decide further if you are at a local minimum or a maximum, you need additional information, right. So, you need, it is not just enough that you do not have a component along that the gradient does not have a component along the tangent space. What also matters is whether you have approached the tangent space, that point, along an increasing curve or a decreasing curve, right. So, that is what we need to check. So, something analogous to the second derivative condition of scalar optimization has to be invoked. So, let me state that now. Suppose x star is a local maximum of your optimization problem, which is maximizing f0 of x subject to fi of x equal to alpha I for all I. And suppose the gradients of the constraints are linearly independent. Now, let lambda star be such that those equations are satisfied. Let lambda star be such that this condition is satisfied. And define C of x star lambda star as this. It's all directions D such that this is that tangent space that I was referring to. It's those directions D such that they are orthogonal to all of these gradients, right. This is the tangent space. Okay, then if it is a local maximum, then if f0, f1 dot fm are twice continuously differentiable, then you can write then the following must be true. You can take W transpose So, I'll explain what this notation is. This is another piece of notation. Now, here this L here, L of this is the function defined as so this is your second order condition, which tells you that if you have found some a condition which satisfies the previous condition, found a point that satisfies the previous condition, that means this boxed, it satisfies the constraint and you have it satisfies all this. Okay. So, then now if it is a local maximum and you know that your functions are twice continuously differentiable, then this must also hold. That what is this? This is looking at the Hessian of this function L. L is found by taking a linear combination of the objective with the constraints. Okay. It is found by taking a linear combination of the objective with the constraints. So, let me just make there is a small correction here. So, this should be a negative here, and I should write this as okay. So, what you need to look at, what you do is look at this function L, which is formed by taking the objective function along with the a linear combination of the constraints. So, you take f0 of x minus lambda 1 f1 lambda 2 f2 dot minus lambda m fm. Put all of that together, that is called this function L. It has a name, it is called the Lagrangian function. You take the Lagrangian function, look at it only in the x space. It's a function of both x and lambda. You take the Lagrangian function and look at it only in the x space. Calculate the Hessian of the Lagrangian only with respect to x. Okay, assuming lambda fixed, you just think of it as a function of x. Calculate the Hessian of the Lagrangian with respect to x. Evaluate that Hessian at x star lambda star. All right. And then you look at this thing, this looks like, so what is this? This is W transpose Hessian of the x Hessian of the Lagrangian times W. That has to be less than equal to 0 for all W that lie in this tangent space. So, which means that the function should have a certain curvature along the tangent space defined by the constraint. Okay, the second order derivative of the Lagrangian is telling you how the Lagrangian curves in the x space, but then we want, it is necessary that this is less than equal to 0 along the directions defined by the tangent space of the constraint. Is this clear? So, this is the thing that is this is one way of further reducing the number of further pruning from the set of points that satisfy these boxed constraints, boxed equations. So, you when you get an optimization problem, you try to solve for this, you can you are looking for an x star and a lambda star, that so they will you will be able you need to satisfy the constraints and you need to satisfy this boxed equation, but then this could still get you to a local minimum or a local maximum. Now, if you are looking for a local maximum, then you will further check if your point satisfies this condition. Okay. But for you to check this, you need that your functions are twice continuously differentiable. Okay. Like so this is a necessary condition. The sufficient condition meaning that if you want to be sure that it is a local maximum, then what you need to do is the same thing here gets replaced by a strict inequality. For all w in this set C star x of C of x star lambda star, w not equal to 0. So, what this means is that this what we are referring to is that this Hessian should be negative semi-definite along a certain subspace only, not necessarily along the full space. We just need that it's negative semi-definite along that particular subspace. So, sufficient. This is a sufficient condition. So, if this is less than 0 for all w in this, then is a local maximum. Okay.